let's continue. So hopefully we agree that this is a red-black tree. So it is not perfect, obviously, because it's not. Is it full? No, and also it's not complete. Remember, the full was meaning 0. We have some parents with only one child. Single child parents which are not allowed basically. So none of these are true, but it is a proper red-black tree. And again, it seems a little bit out of balance, right? Doesn't it? But still, it is. For red-black trees, it's balanced enough. It actually has pretty good performance, right? Still going to be log n performance, actually, right? So it is red-black. So, but let's look at the implications of these rules. So, if a red node has any children, so this means it must have the children must be black, right? We know that, but they must be 2, right? Of course, first they have to be black. That's part of the rules. But why you must have 2? That's a good question now, right? So. Let's explore this first one. I'm gonna do one more paint. Right? Do more paint, right? So I'll do it like this, right? Maybe like this. Yeah, that will work, and this one will work as well, right? Yeah. Maybe can we adjust this? No, I thought we could adjust it. Okay, so maybe not. All right. I guess I'll download. This will be easier. All right, download it by trees. Come on, I don't want this. Okay. Right, these are the implications. Okay. So, the rules. So, any children, they must be black. Let's think why. So, I have a. Right, so this, I guess I should make it black. Yes. Make obvious, right? So root is always black, right? Okay. So if we go to the red, right? And you don't have it because you can make a red, right? So black nodes have red or black children, right? So all, right? So say we have a red child, right? Right? So and let's just put the numbers here, right? This will be like 5, and this will be I guess 10. That's fine. Okay, so 2 children. So why must we have 2? Why must we have 2? Let's say we have 3, and here we'll have, I don't know, 7, right? So why must we, so right now, you have only one child, right? This breaks, right? So right now, we have an x with 1, right? With an extra 1, 2, right? So how many blacks we have? 1 and 2 blacks, right? 1 black, 2 black. Here you have 1 and that's it, right? So you must add it. Still, is this a red-black tree, by the way? Question to you. Is this a red-black tree? What do you think? Is it a red-black tree? Is it or not? Its root is black, we have red-black node, we have the binary tertiary, that's fine, right? I didn't make a mistake, I hope. And also, look at the balance. Now the problem is, this is the trickiest one, right? This is the only tricky part is that right now, yeah, this looks good too, right? We have 1, 2, 1, 2, but the issue is here, right? We have only 1, there's nothing here. So in order to be red-black tree, you have to have something here like 18, right? So right now it's red-black tree, right? So you need 2 and 2 here, right? So as soon as you add something black on one side, every other place, every other path must have same number of black nodes, right? So this leaves it. So let's look at the second rule. If black node has only one child, that must be a red leaf, right? Why? Because why? Again, usually you can add red, no cost, right? But I cannot. If I add this black, I must add another black because we have created new path, right? You must, right? So you might be asking, so why would only one child, right? It's only one child. If I have another child, you can start balancing, right? If it's only one child, you must, because why? Because this creates an imbalance here, right? Now let's see, this would be like 16, right? So this is not a red black anymore for a couple of reasons. Because why? Because we have, right? We have this, this, right? 3 black nodes, 3 black nodes. And that's the rule, right? That's the rules of red, black, green. And again, the rules are for purpose of keeping some sort of balance, right? So two, right? You know, two, right? And also here, two, right? Also, right? Remember, this also counts as axis, basically, right? So 0 or 1 axis, right? So here, this is the imbalance, so we have to add black here, but that's not all. You have to add other blacks here as well. So this basically completely ruins the thing already, right? So the usual, this is a bad idea actually here, right? Instead, this should have been a red. Then we keep keeping this balance. So again, yeah, usually try to add as many red leaves, red leaves or red nodes as much as possible, right? Because well, then you don't have this extra rule. Okay. Hopefully you can see this sort of like this follow-up, right? So let's keep looking at this. Right. So maximum height. So this leads us to the fact that this is like the worst case scenario, right? Basically, I want to copy this and then I can make a paint of this. I think I can. Right? Let's see if I can do this, right? Or maybe or I can maybe do some markup here, right? Better do that because instead of doing it on a smart board. See, I think I can. Control. Oh no, Control C. No, I want to see this. No, I don't want to fill in forms. I want to just basically draw free. Can I do draft here? Yeah, I can. Oh yeah, I can. Oh yeah, I can do this also here actually, right? Yep. Okay. So I can do this then. Yeah. Okay. Cool. Yeah. Right. So Control Z. Right. Right. Okay. Right. So this is the maximum height you can get. So in this first one, you start and you have this red black tree. You check with the binary search, right? And again, 14. Well, that's in mind. Yeah, looks good. 35. Yeah, looks good. Yeah, looks good. Again, I don't see any obvious mistakes. Now, red black, yes. Do reds have only black children? Yes or nothing? That's fine. Is this perfect binary? No. Is it full? No. Is it complete? No, of course. Right? Don't always here. But it is relatively balanced. It's simply full of black nodes, right? So this demonstrates actually like the maximum. This is like the maximum height or maximum imbalance, right? So on the left side, I'm getting email. Right, so let's count this, right? So 1, right? So that's 3, right? 3 black. Here. Again, 3 again. So we're good. How about here? Let's put it over fast. 1, right? 2, 3. 3 black. Again. Again, 3 black. How about here? This gets a little trickier now. So these are so another exit. This is also a possible exit. So another 3 black. Okay. How about here? So how many more exits we have? Well, let's have 3 exits here. Let's say 1. So this is again 1, 2, 3. So 3 black. And here the tricky part here, which is going to miss, is that here you go 1, 2, right here, right. You have exit here. This is also 3 black, right. And of course, because this is single parent, right. Single parents, they also get this also counts as exit. And here, right, or fast. And exit or fast, because I'm calling exit, is basically represents fast. So 1, 2, 3. And this of course also has 3 black. So this is the maximum 3 black. Come on. 3 black. Right? So this meets all the requirements as defined, like I said, 45 years ago, or almost 45 years ago, of red, black, 3. So yeah, so it is not perfectly balanced, but it is good enough, right? So this is one. So height, how much height? I guess depth or height, right? I would call it 2, right? So here we do different colors, 2 different colors. Right, height, right, so here, right, I would say, well, it doesn't matter how it counts, 2 or depth or height, I guess two hops, right? Two hops, right? Here we have a 1, 2, 3, 4, 5 hives here, right? So here, right? 5 hops, 5 hops, right? So 2 to 5, right? That's like the worst case scenario, right? Or you say 3 to 6, I guess, right? 3 to 6. It depends on the count, right? So I think the book, let's see what the book says about all of this good stuff, right? Let's look at the next slide. Let's see the next slide. I think I'll exit this cancel. I'm not going to share this. And I can go next. Okay, yeah. So yeah, I think so. Yeah. So insertion. So yeah. So maintaining the red-black properties. So you must maintain rules of red-black tree. So new node is always a leaf, of course. What's a leaf? Leaf is a node with no children, right? Leaf. So so new node must be always leaf. This means it cannot be black because you are going to immediately violate the rule 4. Why? Why are we going to modify? I want to figure this out. Here, right? Because we insert one black, one black, right? One black, right? The other children do not have 0 black, right? We imbalance immediately, right? Imbalance, right? So, must be red on if your parent is black. That's easy, right? You're completely done. So this is the best case scenario, right? Red, black, easy case insertion. So unfortunately, eventually you're going to have a problem if you don't have a parent red. So this now things get interesting, right? Interesting, right? Meaning you will not be able to do this implementation. Maybe with ChatGPT you could, right? But it will be really tricky. So things get, I would say, interesting, meaning tricky. How tricky we'll see, right? So insertions with red parent child. So let's say where we're going to do this, right? Let's see where we want to insert it, right? So if I insert, I can insert here, no problem. So I could do like 8. Or I guess I should do red here, of course, right? I'll do red, right? So something like this. This is completely fine, no problem. Here also. So I have like 1, 2, 3, 4, 5 places where I can do anything I want, right? Do anything I want, right? So here also I could do like how much I can put here. Oh no, that's 8. By the way, nobody called this. This is an error. Why is this an error? Because 8 does not go here, right? 8, I could put 12 here, right? Control Z, right? Control Z, it should be 12 or something, right? 8 would go here, and it would be a difficult choice, actually, right? So well, in this case, we have about half of the 8 possible points of entry or insertion are fine for red, right? But eventually, of course, you run out of this choice, right? So right now, if I have to insert something like 6 here, well, I'll have to do recolor, right? So that this leads to the fundamental idea behind balancing. At some point, all these algorithms, we'll look at another one next week, AVL trees, you need to rebalance or rotate some things. You can do recoloring, sometimes you do color change, and sometimes you do rotation. In red-black trees, you don't have color change, which are relatively easy to implement. Let's look at examples, right? So if you have settling of parents black, right? Let's look at this. So this is a simple example, right? So here X, we're inserting X, right? This actually, first of all, doesn't look like. First of all, this part here is bad already, right? Let's look at some visualizations. This is going to be probably better if you do it on a red-black visualization. So let's do this here, right? So insert how much? Let's do 10, right? Do you want to show red moves, right? Do you want to show? Yeah, now leaf, now leaf. But we don't want to show them. Okay. So this is a red-black tree. Why? Because we have the root is red. Okay. So root is black. Sorry. Root is black. So if I insert, let's say insert 16, right? I'll insert 16. So where is it going to go? To the right here. And what color is going to be? It should be red, right? Why? Why? Maybe I should pause it, right? So I'll delete 16 as well. So, first of all, this leads to the second rule, corollary. If you find a red node, right, and it's a leaf, we can safely delete and nothing breaks, right? This is a leaf. 16 is a leaf, so delete, right? We have to find it first, right? Looking at the right subtree, yeah, there it is, right? We can. It's a red node. It's a leaf, and we can delete it, right? Because it's red leaf. Okay, so what do I want to do now? I want to insert 5 or 6. So it's going to be what color? What color is going to be 6? You can't see it? Right. I mean, it's a red. Again, root is red. Root is black. Root is black. Remember, we need the balance. We cannot insert single black. We have to insert red. So it's going to be red. And it costs us nothing, basically. It's a really easy case, right? This is like an almost trivial case, right? As long as you know what BSTs work. So, let's insert 14, right? So, 14 is also going to be red, right? No problem. Right? Now, okay, that's fine. But now we have a problem. Now we basically have reached the current levels. That's the best we can do, right? Why? Because next time I insert something is going to be black. And that's going to lead to some big problems. I'll show you. So, what number do you want to insert? Give me a number. 5. Okay, let's do 5. Sure. Let's do 5. So I'll insert 5. So we know where it's going to be. It's going to go here. Unfortunately, red parents cannot have, it has to have black children, right? But that breaks the symmetry, right? Let's see this. Insert 5, fine, okay, it's red. You say, okay, by default red, but this cannot stay because reds have to have black. So we need to do some coloring changes. Let's take a look, right? So, what can we do, right? Found null inserting element, right? Node and parent opposite. Uncle of node is red, right? So push blackness down from grandparent. I love this. I love these explanations. So who is the uncle? I wish they would tell you who the uncle is, but in this case, the uncle is this guy here. So this is father, right? And that's like a brother of the right. That's the uncle. The 14 is the uncle of number 5, right? Sort of makes sense. So this means is look at this. Push blackness down from the grandparent. So this is the grandparent, right? They have 2 children, 6 and 14. I assume in this case, let's say male, right? Uncle, right? Maybe aunt, and right? So what we can do here, this is still a good case. Why? We can replace these both with black. Easy case, right? Look at this blackness. And that's it. Okay, we say, okay, we push the blackness down. Well, we're not done yet because the root has to be black as well. That's easy to fix, right? We just make it black, right? Root 3 is red, let's color it black, and that's it. And we are done. But we gain this extra level of blackness, basically, right? Now, so now again, we have how many paths of exit do we have here, right? We have this one here, one, another one here, by the way, right? And another one here, right? So 3 possible exits on which lead to the, and they all have two black nodes in each path. So let's insert a few more, right? Let's insert a few more. Give me a number. 15. Okay, so it's gonna go here, right? So what color is gonna be? Yeah, because by default we start. Okay, in this particular case we start with red because let's hope it stays red because then you don't have to do anything. Let's insert 15. Right? And I'm predicting it's going to stay red, right? Because it does not break anything. Alright. Alright, let's do something harder. Let's insert, like, I don't know, 20? Let's insert 20. So, the problem is, of course, that now we'll have a couple problems on our hands, right? Let's take a look at this, how it's going to be solved. So, first of all, we start with red, right? Insert, right? Step forward. Right? It's so far so well. It's 2 reds in a row is not possible. Right? So this has to be black.
But then we have a problem. If this is black, then your sides don't match the balance. You go to yes, we have to do some recoloring, or maybe it will be something more interesting. You'll do some rotation. Let's take a look. This is where the actual algorithm starts working. We're gonna rotate. As I'm predicting, this 14 will go down here, right? And 15 will be the parent here, right? Because you can rotate this. This is the cool thing here, right? So look at this here, right? Uh, yeah, single rotation. So look at this. Node and parent are both red. Node is right child. Parent is right child. We can fix extra redness in the single rotation. So this is going to be the new black. Red is going to be new black here. And 14 will go down. Let's take a look. You see? Not yet. Now. Now we're good. Let's go back. Okay. So 40. So parent can become a child basically here, right? Because it was bigger, so it has to go to the left, right? And you can insert. So basically, on this we have to finish, of course, then we can move it back to the blackness here, and we are done, right? So this is what ensures that the tree stays balanced, right? Not that, because just coloring is not enough, you need to actually do some rotations. And it's been proven that this number of these rotations is not significant enough, right? Your algorithm, your search, insertion, deletion, all stay log n on average, basically. Yes, occasionally there will be some heavy rotation, but it doesn't break the general performance, basically, right? So you get the best of the both worlds. That you have, it works for any type of data, right? And you have good enough. It's not going to be as good performance as perfect binary tree, search tree, but it will work well enough. But for full, we have like 10 minutes left. There are like 4 cases, right, for these rotations, right? You look at these materials, right? I'm not gonna. It's not gonna be on an exam. Like I won't ask you implement this, right? Because of course usually somebody does, unless you do a bachelor's on binary trees, right? Probably not gonna be. You won't have to do it yourself, hopefully, unless of course like you want to go for Google, right? So, but okay, right. So this is the one case, right? So you can do this move here, right? Single rotation, right? And we rotate, right? But of course I don't like these colorings here, right? So let's look at some other case we can look at. So this was a single parent. So how about if I do 18? Let's do 18, right? If you insert 20, it will be similar, right? But let's do, we can change, so let's insert 18. This is going to be interesting, right? So insert 18. We know where it wants to go, right? It has to go here, right? But this is really weird, right? So how can we change this to, again, we want to, could we push the, well, I think we can just recolor, I think, right? No, unfortunately not, or can we? No, I think we can. Can we switch? Okay, I'm thinking now. Can we just fix this part with the coloring? I think yes. If the 14 and 20 become black, and 15 is now red, that will work. Yeah, because remember, as long as reds have 2 black, that's fine, right? 1 is not allowed, right? So let's do this. See, uncle of the node is red, right? So both siblings are red. We can push the blackness. We push the blackness down. I love this explanation, right? If 2 reds can be replaced by 1 black, basically, right? And now we solved it. Okay, so this is easier than I wanted, but I want to make it more unbalanced. Okay, so let's insert 19. I want to make things harder. 19, insert. Okay, let's go. Let's go on 19. Okay, so what do we do here? What do we here? Well, we'll need to rotate, unfortunately. So what kind of rotation can we do? Let's think about it. Well, we have enough room for 2 reds, right? So we basically need this part, these 3 here. We need to keep, so basically this has to be, we need a new parent, right? Which one could it be? It could be 19, I believe, right? It could be 19. Yeah, and 20 will go here. Yeah, I think so. This will be like a grandchild becomes a parent. Kind of weird, right? So let's take a look. Yeah, node and parent both red. Node right child, parent left child. So it's left, right. Okay, is this good? No. We do one more rotation. Yeah, like I said, we're almost done. And this is gonna be black and this is gonna be red, right? Yep, and now we're done. Right, so 2 rotations. So this was like basically the worst case scenario, right? Okay, and now let's do something really difficult. How about inserting 12? What do we do? Well, not a problem, right? You say, okay, we want to insert here, but if you insert 12, where is it gonna go? 12 is really easy. It's gonna go here, right? Right? Then, right? Okay, let's do 12. That's easy. We don't have to do anything, right? Here, it's red. Easy, easy, easy. Now again, let's do 11. So if I insert 11, what's gonna happen? I'm going to start 11. It's going to be red. We'll need to rotate. And 12 will be the new parent. It's going to be black. And 14 will be red. And 11 will be red. Let's see if I'm right. 11. Insert. It has to go here, right? No other place. 15, less than 14, less than 12. We have red. So this part here will rotate. So 12 will go up, 14 will go down, right? Single rotation. Single rotation indeed. Like this. Almost done. 12 will be black. And again, so we keep both properties. Reds have 0 or 2 black children, right? That's fine. And we have equal number of black paths. 2, 1, 2, 1, 2. We have 6 exits. 1 exit, 1 exit, 1 exit, 1 exit. 6 possible exits, but they all have same number of black nodes in the path. 2 in this case. Alright. I guess one more and then we finished, I think. Let's insert something. So anywhere here will lead to problems, right? This is the hardest place. Here it's all, you can still do some stuff, but this is like full. This side is full, and this will require some heavy rotation. So what number? So anything over 10. So what number should we insert? 6, how much? 13. So it should go here, right? Let's see if this, can it be fixed? I don't think so. We'll need to have extra black basically, right? So this is the worst case scenario, I think. So it should go here, right? Easy, easy. Here. Okay, that cannot stay. Let's keep going. We'll do some rotations. Our uncle of note is that we're gonna push the blackness here, right? We push blackness down. I love this, yeah. Okay. Are we done? Unfortunately, we are not done. Why? Because this is a problem. We have a problem here, right? You cannot have 2 reds in a row, right? So, node and parent are both red. Node is left child, parent is right child. So what do we need to, you see this one? Wow. Right, are we done? So we can replace this, right? 12 can go here, 15 can go here. Let's check it out, right? Now, are we done? Unfortunately, no. Right? It's still not finished. Now we need another rotation. This is going to rotate. Wow. On this rotate. So we perform 3 rotations, right? And again, doing this by hand, coming up with these rules. There's like 6 or 8 rules for red black trees. So that's relatively easy in a way, right? But again, the approach is that we can always make a rotation. I mean, you can show. You can look at this simple example. Even if your tree is really big and long, right? You can still do these rotations. You might need to go up all the way log n times, right? With height maybe 10 or 20, right? You have million items. It's about height is like 20 something, right? So you need to go up 20 times. That's still log n operation. So worst case scenario, your insertion will take log n rotations, which is complexity is log n, right? So each rotation maybe takes like a couple operations. You know, that's a constant, right? You know, 3. You always rotate 3 elements, right? So pretty amazing actually, right? So I think that concludes today. Do the quiz for today. On Tuesday we will do another alternative balance tree, which is slightly more expensive as memory, but I think maybe it's slightly easier actually, maybe, right? Also, it's actually a little bit older, and also it could be a good alternative to red black tree. So, how about today? What do I want from you? What do I still want from you? Well, where is my Here we go, right? So we have a homework, right? And this is easy homework. Well, relatively easy. It's because it's in famous two-sum problem, right? So you'll be reading a text file, yeah, and you need to find a format. Okay, let's check this out. It's when is it due? 5th of November. That's kind of. Can you make it? No. No, I don't think so. Do you have time machine? Why did I put it? I think I meant 5th of December, by the way. I'm pretty sure, right? Yeah, I did mean it. So nobody told me about this. Okay. So this is one of the more famous, interview problems. But let's check this out. Right. So this is what you need to find. You have a bunch of numbers, right? And you need to find this target. So which numbers add up to this target, basically, right? So you do this in brute force, and that will give you only 4, right? You do brute force 2 loops, right? You can do this 2 loops. It's not gonna break your machine, right? But it's gonna give you 4 because it's too easy, right? If you do this, anybody could do this, right? But if you do n-log solution, well, 70%. Well, actually, I would say this is one of those cases where 70% is kind of obvious, right? You can do sort and then pick up, right, the numbers, check it. That will work, but there is an ON solution, right? And it involves a hashing structure, right? A map, right? So, unordered map, by the way, right? Or because that's n log n, right? Extra complexity, right? So, relatively kind of neat problem, right? So, idea at least behind. So basically, use some sort of hashing structure. You won't get full 100% in this exercise. Okay. All right, guys. So I'll see you on Tuesday. Have a good weekend, everyone. All right.